Okay, let's talk about Fundamental Theorem of Calculus. And it's titled this, but I'm going to actually state the Fundamental Theorem of Calculus much later. Let's talk about the following problem. Let's say you have a function f of x, and for the time being, we'll only talk about functions that are positive. Later, we will talk about functions that does fall below the x-axis, but let's just think about the functions that are above the x-axis. And let's think about an interval a to b, and the question is, how do we get the area here? The question is, how do we get the area under the function, under the graph of the function over the interval a to b? Now, I'm going to introduce a notation. We are going to denote this area by this notation, a to b, this s that's elongated, f of x dx, and this is called the definite interval. This is called the definite interval. And the Fundamental Theorem of Calculus has to do with this definite interval. Okay. And actually, let's just make this a and b to be also positive, just for simplicity of the discussion. And we're going to work our way through this question, and eventually you will find the answer to this problem, and that will be called the Fundamental Theorem of Calculus. All right, so to approach this, we're going to make the following function. Define I'll just call it s of x as, I'll call it capital F. So capital F of x as the area shown below. And as a picture, it's simply the same function, but it's the area from 0 to x. Okay. So at the moment, it's vaguely related. This is also talking about the area, that's also talking about the area. Whereas this one, it's not the interval from a to b, it's from 0 to anything. X can change, right? X can be x equal to b or a or even something in the middle, or it could be like 100 or 1,000. So you just make x vary. Okay. And we're going to study this function using the same principle that we talked about when we talked about the differentiating the area with respect to the radius of a circle, right? So we learned that if you take the area of a circle pi r squared, and if you differentiate pi r squared with respect to r, you get 2 pi r, which is the circumference of the circle. That's because every time you increase, what's being accumulated? It's the circumference that keeps being accumulated. As you thicken this, your circumferences are getting added on. That's why this happens, right? So we're going to use the same idea here and ask the following question. What is df dx? I wonder who already knows the answer. If not, it's okay, because we will continue to draw pictures. But does anyone actually know the answer or have an idea what that could be? Not yet? All right. So in that case, let's draw a picture and see what happens. Okay, dx here, dx means an infinitesimal increase in x, right? Which means this x is increased ever so slightly. So this much is dx. And then f is the area from 0 to x, but this time x is increased to x plus dx, so the new area is the area from here to here. Then what is df? df is the increase of the area as you go from x to x plus dx, right? So you can shade this part right here, and this part right here is your df. Okay. Now imagine that this is very, very thin. dx is like a practically zero amount that you increase, right? So that this looks like a very tiny little rectangle. Okay. How do you get the area of a rectangle? Okay. So what's the base length of this rectangle? Dx, right? So we know that df must equal to dx base times height. Oh, wait. How do you get the height? Oh, there's something that I didn't tell you. This graph is what? This graph is y equals to f of x, right? Okay, so if you know that, what's the height? fx, that's the height, right? See, this length right here, above x, this is f of x, right? That length is f of x, and you multiply by dx to thicken it. That is the increase in the area. Okay? And now you divide by dx, and you get this awesome result, which has a name. So if you divide by the dx, then you get df over dx equals to small f of x. Now, I may want to spend more time on this one, but because I don't have enough time to do the other ones today, I'll just say that this is what we call Fundamental Theorem of Calculus 2. And we will speak about Fundamental Theorem of Calculus later. It's a small modification, but all it's saying is the following. The area function, where the x increases, right? If you have such an area function, the derivative actually gives you the function itself. And that's a pretty cool result, because that says capital F is merely an antiderivative of f, right? All right. Next, what we want to do is we can now use this to find the original question. So here's the answer. Here's the answer to this question. Right? Let's say we solved this. Right? We solved an antiderivative problem before, right? If you're given the derivative, you can find the antiderivative. Let's say we solve this. Okay? Then the next question is, can we actually use to find the answer to this question? And here's a nice way to think about it. Here's a way to visualize it. So instead of thinking about the area from A to B, just think about it as area from 0 to B. Okay. Can you represent this using F, capital F? What is it? F at?
It would be f of x.
At?
0.
No. 0 is always fixed.
Oh, at b.
F of b, yes. This will be f of b because this is the area from 0 to b. remember, our definition of f of x is what? Area from 0 to x. Right? This is the area from 0 to b. It's f of b. Okay. Now, what about 0 to a? What would this be?
That'd be f of a.
F of a. Okay. Once I have this and this, how can we get this area? That's exactly right. Okay. So what we just proved is that if you want the area from a to b, f of x dx, then all you have to do is subtract. Okay, so first, f is any antiderivative. Now, I'm actually slightly skipping a step. Let me explain after I write this. Okay. So if f is any antiderivative of small f of x, then we just found out that you can find the area under the graph of f from a to b by first evaluating the function, the antiderivative at b, minus the antiderivative at a and subtracting it. And that gives you the area. Now the thing that I just skipped is that here, this one is a specific initial value problem because in this picture, what is f of 0? If you have an area from 0 to 0, what would that be? It should be 0 because there's no interval, right? So you're given an antiderivative and you're given an initial value. That's an initial value problem which will have just one particular solution, not in general, right? However, this 0 can be anything else. You could just write this 0 as some other value c, and from c to x, and the same kind of argument will hold. So this condition, which seemed to be crucial in our argument, was just there so that we can make sense of things easier. Because if that's like c, it's harder to think, right? So that's like the small part that I skipped, but probably you didn't really go this. But that's what's happening in general. And this is called what? This is called the Fundamental Theorem of Calculus. It's an awesome theorem because it starts to give you answers that you didn't know. So here's a very simple one. I don't want to give you anything harder because I just want to demonstrate this. So let's say find the area under the graph of y equals to x squared over 0 to 1. Okay. Then in the picture, this is from 0 to 1, and this is the area that you're looking for. Oh, by the way, what is this coordinate right here? 1, 1, right? If you plug in 1, you get 1, so it's 1, 1. All right, I claim that without doing any calculation, this has to be less than 1/2. Do you see it? Why would that be true? Can somebody explain why this area better be less than 1/2?
Because because if the area was 2, then it would have been shaded in completely. And if it was less than 1/2, simply pushing past the grades because it's from 0 to 1. If that makes sense.
Yes?
Is it like if you made like a rectangle and look for the whole area?
This will be 1, right? But I'm claiming this should be less than 1/2. Why?
It's not a straight line.
It's throw a straight line, right? You get a triangle. What's the area of a triangle? Base times height times half, right? It's 1 times 1 times 1/2. So the answer must be less than 1/2, right? That's something nice to know, because if we get something else, if something that's bigger than 1/2, then we know that our answer is wrong, right? Well, actually, how do we get the answer? Well, we use this formula, the fundamental theorem of calculus, which is you integrate from 0 to 1 of x squared, which is our function. The function is f of x is x squared times dx. And the way you get it is explained here, which is the antiderivative of 1/3 x cubed. It's just by adding 1 to the exponent and putting the reciprocal in front. And let me give you a new notation. The notation, when you have a bar and 0 to 1 like this, means that you're supposed to take the first top number, plug it in, minus the bottom number plugged in. Okay? Top number plugged in minus bottom number plugged in. That's what it means. That captures this right side. Okay? So that's an easier way to express things, which is 1/3, 1 cubed, minus 1/3, 0 cubed, and that's equal to just 1/3. Indeed, 1/3 is less than 1/2, right? And it does, I mean, I would agree that if somebody told me this is 1/3, I would accept it. So that's indeed the answer. Okay, now the final remark here is that I've been talking about the meaning of dx. And if you look at this integral from a to b of f of x dx, this symbol actually has a lot of thought put into it. So first of all, dx is this very small increment in the x direction, right? And what is f of x? That's the height of a rectangle at x, right? At x, this height will be f of x, right? So you by multiplying these two, you get a very thin strip area. And what are you doing? You're adding this s is from summation. It's s for summation. Okay, summation of all these tiny rectangles from A to B. Okay, so it's like here, and you have all these tiny rectangles, and you add them up. That's why this is the area. And this is actually true in general. In many of the application problems, we're going to see that we solve problems using calculus by saying that the entire thing is sum of small bits and parts of it. Or dA is like this small bits of area, and you add them up from A to B. And if you actually think about what this dA is, well, as I explained, dA is f of x times dx, right? So that's how this notation makes sense. And on top of that, I'm actually doing this not in the order that's generally taught. In many calculus classes, they are going to introduce this area concept, and they're going to start talking about sigma notation and how to approximate this area. And that's more complicated, and that idea is called Riemann sums. I'm going to do the Riemann sums after we do this, okay, because I want to quickly go over the calculations, and then we're going to talk about the Riemann sums. Riemann sums are, in some sense, stronger than this fundamental theorem of calculus because, unfortunately, not all functions have the antiderivatives. That's another thing that we're going to learn. So, like simple functions like sine x over x, it looks so simple that you think there should be an antiderivative for this. Well, there isn't. Okay? You can't express this antiderivative using any of the regular functions. If you don't believe me, you can go to wolframalpha.com. Do you know that website? That's where you can get help from homework. Okay? Right. So sine x over x, if you put it there and find the antiderivative, it's going to say something strange. Okay? So because of that, although this fundamental theorem of calculus seems to be very powerful, it has its limitations. And because of that, in some cases, you can only approximate the area. And that part is called the Riemann sums, and we'll talk about that after the first exam.